Yeah, so hey, welcome to GreenTalk number 4. I'd like to welcome today Dr. Siddharth Narayan. Sid did his undergraduate university at University in Chennai, southeastern India, in civil engineering. He then did a master's program in the Netherlands focused on research and engineering and ecology in estuaries, and then a PhD in the United Kingdom, I believe. At the moment, he is a researcher, a scholar at University of California, Santa Cruz, just down the road. And he's going to be talking today about melding ideas of ecology and engineering and project design, looking at problems to do with population, sea level rise, ecological change in estuaries around the world. So I'd like you to give him a warm welcome. Thanks very much.
Thank you, Josh. Thanks for having me here, and thank you all. I'd like to talk to you today about reducing risks on the coast and how coastal engineers are looking towards nature-based solutions to do that. And so this is essentially multidisciplinary, and I'm going to try and paint a picture of how engineers, ecologists, and economists can work together to bring theory to action. I'll start off with a brief introduction about myself, about UC Santa Cruz, and the Nature Conservancy. I cannot do this without my team, Dania Tres-Palacios at the Nature Conservancy, Professor Michael Beck, who's a TNC scientist and is also adjunct professor at UC Santa Cruz, and my fellow coastal engineer, Borja Reguero, who's also at UC Santa Cruz and TNC. So to start off, this is our campus. This is the Long Marine Lab at UC Santa Cruz, and it's a pretty picture when you're in a helicopter flying over it, but you have the ocean at our doorstep. But as the case often happens, that's usually me, and that's what my day looks like. I'm in a little trailer staring at a computer in this beautiful location. Though I do admit I can walk out for lunch to the cliff. So this is the Long Marine Lab of the UC Santa Cruz, and it's sort of a place where a lot of coastal and marine science happens within the UC Santa Cruz system. And our team, Mike, Borja, Tanya, and me, we're also affiliated with the Nature Conservancy, which is an NGO. The Nature Conservancy is basically this giant NGO across 69 countries, but with their focus in the US. And their mission is essentially to conserve the lands and waters on which all life depends. And so that's natural life and human life. And so that's their overarching goal. And within TNC, there's what's called the Coastal Resilience Program. And this program, the main focus of this program is to examine the role of nature in reducing risks on the coast to people, and at the same time trying to understand how we can better understand the natural habitats that we have on the coast to restore and conserve them. And also to communicate this to people, to develop tools, but all of that around examining nature's role in reducing coastal flood risk. And this here, for instance, is one example that the Coastal Resilience Program, one example of their work. It's guidelines for coastal protection services of mangroves and coral reefs that we helped develop with the World Bank in the Philippines. So that's just one example of the kind of very broad-based work that happens here. So I'm going to now take a step back and introduce coastal engineering as a subject. Now, I'd done my civil engineering in India, and I had never heard of coastal engineering until I actually started doing a master's in it. So what is coastal engineering? Well, I was doing some preparation before this talk, and I realized that human beings have been engineering for millennia. This is a photograph of a dockyard in Lothal in India, in the northwest of India, which is the Indus Valley civilization. And this is from 2000. This has been dated to 2300 BC. And you can, this is from the Penn State website, and they have a quote there where it says, "The high degree of engineering skill achieved can be understood from the ways in which they regulate the flow of water into the dock, at low and high tides and ensure that ships float by opening this door in a vertical groove to allow excess water out into a spillway. So this was happening in 2300 BC. And you also have, for instance, in 1900 BC, the port of Alexandria in Egypt. And in 700 BC, the city of Ostia Antica in Rome. All of these were basically engineering structures that were built on the coastline to allow trade, essentially to facilitate the movement of ships and to facilitate trade. And so all of these would have required sort of basic knowledge of ship traffic, of water levels, of the interaction between the tides and the river discharge, and also of the interactions between the structure and water. So this is just to say that this has been going on for a long while. Fast forward a lot to the 1900s, and in 1953, in the Netherlands, there was a massive disaster. It's called the 1953 North Sea flood, and this affected the Netherlands and Europe, and about 1,800 people were killed in the Netherlands, several thousand buildings damaged. A large part of the affected area was agricultural, and a lot of animals drowned. And this is when the shift began in coastal engineering from just ports and harbors to more looking at protecting us from rivers and seas, from the threats that rivers and seas bring. So the way that happens, essentially what coastal engineering now mainly focuses on, in addition to ports and harbors, is managing our risks at the coastline. And you can do that basically you can do that in three different ways. You can protect, So you can protect by, for instance, building a structure in front of of whatever house or building that you want to protect and preventing the water from reaching it. You can accommodate, which goes to say you can make space for the threat while still having your structure there. So an example of accommodation would be building your house on stilts. Or you can retreat. So you can just simply move back and let the sea have that space. And in fact, in ancient times, that's probably what a lot of people did. When there was a big flood, they'd move and go back. We're going to focus in this talk on the protect option, which is usually the option that people choose because it's it's sort of difficult for us to say we're just going to move back and let the sea take space, though there can be advantages to that in some cases. So if we're going to talk about protecting the coastline, and if we're going to talk about having structures on the coastline, how does a coastal engineer do this? Like, how do you go from the idea to the execution? So this is basically, I'd say, follows the steps that any civil engineering project would. You have a project need. You evaluate what the baseline conditions are for the project. You identify the goals of your project or the goals of you identify the goals that you would like your structure to achieve. And then you identify various alternatives. Is it going to be a seawall? Is it going to be a levee? Is it going to be a dike? You evaluate the costs and effectiveness of each of those alternatives. You select the best alternatives. And then you go into a more detailed design and see how that design pans out. And quite often, this is going to have to be a loop where you go back. You might find that a design turns out too costly. So then you go back through the alternatives again, eventually come to a final design that you then design and construct. And an important step that's often missed out is to then monitor the performance of your structure and see how it's done in order to learn lessons for the future. So this is the process of, say, designing a coastal engineering project. And this process is going to have to take into account key principles. And many of these principles are sort of, again, engineering principles. So for instance, you need a requisite standard. So if I'm going to build a defense to protect myself from say, 1 in 100-year storm, I need to know that. and make sure that my defense is going to withstand that. The idea here is to control variability. So I'm controlling my variability in my water levels so that the environment behind is protected from that variability. Also, I need to make sure that all of this happens at a reasonable cost. I need to make sure that the structure that I build is actually going to stand and not fail due to some weakness. I'm going to have to make sure that it's reliable against the loads that are imposed on it. And implementability is also important. So for instance, if I'm building a breakwater, I need to make sure that there's access for my trucks to bring the rocks in. And two things that are not as commonly thought about in engineering projects, but are more thought about when you talk about ecosystems, which I'll come to later, are adaptability and resilience. So adaptability, for instance, is the idea that if you build a structure for a certain environment and the environment itself changes, is your structure going to be able to adapt to those changes? And that's becoming increasingly important as sea levels rise at accelerated paces, as storms shift. So structures that we built 10 years ago for certain conditions that we expected 10 years ago may not be able to withstand conditions that we're going to predict happen 20 years from now. And that, again, leads to having the appropriate boundary conditions and loads for which we design these structures. So we need to know what our boundary conditions are. We need to know what our loads are when we design these structures. So since the 1953 flood, there was this shift, both in the Netherlands, exemplified by the Netherlands, but also internationally. And this is a quote from the Dutch River Water Authority after the floods, where he said there was this national feeling of never again, where we said we should safeguard our nation and population from threats from the rivers and seas. And this has been translated into very high standard, highly engineered coastal defenses. Like, for instance, this storm surge barrier in the south of the Netherlands, and this storm surge barrier here in Rotterdam, which is one of the world's largest ports. But again, like I said, it's not just the Netherlands. You have New York planning a new storm surge barrier that's going to cost about $335 million. And this is in direct response to Hurricane Sandy and the flooding that happened there. In the UK, you have the Thames barrier in London that's designed to basically close and protect all of London from flooding during a storm. And these are remarkable structures. Like they're remarkable feats of engineering, all of these structures. But at the same time, they're expensive. These structures are very expensive. So for instance, this is a seawall in New Jersey after Hurricane Sandy. And more on the right, there's a picture of a seawall in San Francisco. And there's a study recently that said that if there were an earthquake and the seawall was damaged, it would cost up to $5 billion to repair the seawall. And so we're increasingly asking ourselves, what do we do if these structures are really expensive, but we still need to come up with some way to protect the coastline behind us? And in parallel, something else happened after the last few major world disasters. So there was the Asian tsunami, there was Typhoon Haiyan in the Philippines, which is devastating to the country, and there was Hurricane Sandy. And after all of these, as an engineer, I would have expected people to say, let's build more walls, let's protect our coasts, similar to what happened in the 1953 floods. But something different happened. In the popular press, there was a lot of attention around nature. People are saying, oh, mangroves shielded us against tsunami and typhoon in the Philippines. This is an example from the Philippines, press coverage around mangroves in the Philippines. And there was a lot of coverage around this. And at the same time, we are beginning to realize that our coastal ecosystems and habitats are at risk. So mangroves are at risk, particularly in Southeast Asia, but generally the world over. And the same is true of coral reefs. And so all of these issues are sort of pushing attention on this field in coastal engineering, which is basically, it goes by several names. I'm going to call it engineering with nature here. It's also called building with nature. But then when you say engineering with nature, it sounds like an oxymoron. How does this work? Like, it's just two completely diametrically opposed things. The fundamental question here that we're talking about when we talk about engineering with nature is, do coastal habitats protect people? And the answer is, yes, they do, but, as is often the case with most answers like that. This is a study from Stanford University where they looked at coastal habitats around the US and ranked them in terms of the people they protect behind them. And you can see that the northeast of the US, for instance, is highly ranked in terms of the number of people protected by coastal habitats, and so is Florida. And you can also see here in the bar graph in the middle, the black is people protected with habitats, and the white is people exposed without habitats. And so you see that if you remove your habitats, Florida, for instance, there's a huge jump in the number of people who are just suddenly exposed to risks with nothing in front of them. And the idea here is that natural habitats form our first line of defense. They may not be enough by themselves, but they do form a first line of defense in areas where they're healthy. And in some ways, this is obvious to someone, say, flying onto an island to surf in the Great Barrier Reef. And you tell them, oh, did you know that coral reefs break waves? And like, yeah, duh. Or even to fishermen living behind coral reefs who've been living there for generations, and they know that that's what the reefs do. The reefs break waves. And they know that it actually shelters their coastline. So in some ways, the knowledge has always been there. It's just that we haven't really explored it. So now if we start formally exploring that and saying, okay, we get that nature can protect the coastline, so what do we do? Like, how do we go about it? And this goes back to the sort of protect, accommodate, retreat options that I spoke about. When you protect your coastline, you can either protect it, you can accommodate the threat, or you can retreat. And combining all of those gives us a whole range of options, from what we call soft solutions, where there's essentially no engineering structure, and you only have, say, a huge grass dune or a massive wetland, all the way towards hard solutions where basically you say, I have no choice but to build a concrete seawall. And in the middle, you have what's called hybrid solutions, where you go, okay, I'm going to mix and match elements of engineering and ecology. So for instance, I could have a mangrove forest, but with a levee behind it, so that the mangrove forest reduces waves, protects the levee, and then the levee stops flooding. Or I can do the same thing with a salt marsh. So you can have these mix and match options, and those are called hybrid solutions here. And for all of these options, in order to we need to study them in order to design them and then implement them. And studying them essentially means understanding the physics, as in how do they protect us, and understanding the economics, as in how much is it going to cost and is it cost effective. And the way we do this is the way we perform any coastal engineering analysis. So you have waves offshore that are driven by our meteorological conditions. We simulate how these waves propagate near shore, so how these waves enter the near shore region. We then see, okay, how do these waves interact with our coastal habitat? Now, that could be a coral reef, it could be an oyster reef, it could be a salt marsh. We study how the wave interacts with the habitat, and then we look at what happens on land. So the wave interacts with the habitat, it's reduced in height. There are some areas, there is still some flooding, so there are some areas that are flooded, and that's the solid red line. And then we ask ourselves, what would happen if that habitat were removed? So what would happen if the coral reef were not there, or if the wetland were not there? And we recalculate the flooding, and we, for instance, find that the flooding is greater and now happens at the dotted red line. And all the houses between those two lines, essentially all the houses that are flooded if the habitat is removed, will give us the value of that habitat. So essentially, you're saying that if the habitat is removed, all these houses here are flooded, and they represent the value of that habitat in providing risk reduction. And so that's essentially how, and then we go, okay, so that coral reef value is equal to the avoided damage from all those houses. And that's the concept that we use essentially in valuing coastal habitats for risk. And this is where you this is what happens if you ask an engineer to model a mangrove forest. This complex ecosystem gets converted into series of cylinders on a little rock with little different water levels. This is actually work that I did for my master's thesis in the Netherlands, looking at a mangrove forest in India. And so this is essentially, we're like, okay, just forget about the complexity. Let's assume that these are all these straight cylinders for now and go with it. But then we still do need information on that ecosystem. So for instance, to decide what the shape of and size of my cylinders are, I need to know what the stem diameter is, what the diameter at breast height is of these trees, what the average height is, what the average water levels are. And so I put all those into my numerical model, and I propagate my waves from offshore to the mangrove forest, and then further on land, and I see that the forest here reduces wave heights. I'm like, okay, good. I know my model is now telling me that the mangroves do reduce wave heights. And I can then quantify this and present it, and I can say, for instance, 2.5 kilometers away from the mangroves on shore, there's still a 60% reduction in my wave heights. And these are cyclone wave heights that I analyzed. It's not regular everyday wave heights. These wave heights are these waves are 4 meters. That's 13 feet. These are high waves. And so we also say, for instance, we talk in terms of annual probability. So very high waves usually have a low probability of occurring. So extreme events occur with low probability. And so, for instance, we can say that a wave height that has a 14% probability, if these mangroves were not there, would become virtually certain. And so removing the mangroves is going to really increase the wave heights and therefore increase damage to places on the coast. So that was one study that I did. I didn't go as far as quantifying the damages, because for that you need information on what the value of your coastal assets are. So I didn't go as far as that in this analysis. But then for my postdoc now, that's funded by Lloyd's of London, who are an insurance agency, who are, believe it or not, interested in this. The question we were asking here is, can coastal wetlands protect properties from flood damages during hurricanes? And this was focused on the US Northeast. And this was a large collaboration. So it was us at UC Santa Cruz with the supervision of Lloyd's and working with RMS, Risk Management Solutions, who are an insurance industry risk modeling firm. So their job is to basically model risks to inform the insurance industry. And specifically in this case, coastal risks from hurricanes. So we said, okay, can wetlands protect properties from damages during hurricanes? The hurricane we looked at was Hurricane Sandy, which took a sharp left and hit New Jersey. This is where Hurricane Sandy made landfall. And here you have a map of New Jersey with the wetlands. And what we did was we ran the model for Hurricane Sandy flooding and damages with the wetlands. And then we said, all right, what happens if we remove the wetlands? What do the flooding and damages look like? And what's the difference in the flooding and damages? And that difference is going to give us the value of our wetlands. And we did this for all the 12 states that were impacted by Sandy. And so this is the result we got. So essentially, we saw that across the 12 states, wetlands avoided damages of $625 million US. And in some areas, it really had a difference, like in New Jersey, where Sandy made landfall. Wetlands made a huge difference in some of these counties. But you can also see that in some other areas, like for instance in New York and Connecticut, there's not that much of a difference. The wetlands don't really make much of a difference. And that's partly because there was less flooding there, but also partly because there are simply less wetlands there. New York is highly urbanized, has lost a lot of its wetlands, and therefore what remains is not enough to make much of a difference. So from this study, these were our main conclusions, that wetlands saved $625 million US. On average, where the wetlands remain, this was about 10% of the damage that happened, even though in total it was just 1% of the total damage from Sandy. And we also, in addition to Sandy, we looked at annual flooding. So we annualized our flood losses using the insurance industry model for several thousand storms. And we found that areas with marshes in Ocean County, New Jersey, saved 16% in their average annual flood losses compared to areas without marshes. And therefore, the final message was that wetland conservation and restoration can and do actually help reduce risk, because it's surprisingly, it's not intuitive to think that a marsh in front is going to reduce your flooding from a house in some instances, but it actually does. So we did the same thing for this was not work I did, this was work that my team did, Borja, Mike, and others. And we did the same thing for coral reefs. They did the same thing for coral reefs globally, where they said, we have a healthy coral reef, and we have a certain flooding that occurs. What happens if we remove the top 1 meter of the coral reef? Or what happens if we lose the top 1 meter of the coral reef due to bleaching? What happens to flood damages then? And therefore, what's the value of keeping this coral reef healthy in terms of coastal risk reduction? And again, this follows the same method, where basically you have your offshore waves with surge and tide included. You bring these near shore to the near shore region, where it interacts with the coral reefs, and then you bring the waves further onto land, and then you estimate the flooding that happens on land, with and without the reef. So in doing all of this, we basically very quickly realized that we need to talk to other disciplines. This is not concrete. And this is nature. I mean, I very quickly realized in my master's work, when I started modeling the mangroves, I was like, okay, I need to go talk to a mangrove ecologist, to someone who knows about this. Because there are several factors that affect the environment in which these ecosystems thrive. And we need a healthy ecosystem in order to get the risk reduction function. So for instance, temperature, salinity, wave exposure, submergence time, light and nutrient availability, all of these affect how healthy our coastal ecosystem is. And there's also issues of zonation or keystone species or biodiversity, in terms of productivity and stability that affect how healthy the ecosystem is. So for instance, with mangroves, you know that there are certain pioneer species that are right out in front in the saltiest part of their ecosystem, which have a different structure, a different geometric structure. And then there are species at the back which have a different geometric structure. And the differences in these structures are going to influence their risk reduction. So we need to understand all of these factors as well, in addition to the traditional engineering processes that we apply. So basically what we need to do is to take all our engineering design principles and then add on the ecological design principles and integrate these two if we're going to actually talk about designing and restoring a nature-based solution. And it's not just the principles, it's the process as well. So for instance, if we have the engineering design process, but if we're going to talk about restoration, we also have the ecological design process where we're saying, okay, we need to restore this habitat. What are we restoring it for? Is our only objective coastal protection, or are we going to have other objectives, like other ecosystem services or simply biodiversity? So we need to take all of that into account. And essentially, this is where engineers and ecologists and economists, in terms of figuring out costs, have to start collaborating. So this is one example of how this could work. So this is in New Jersey, again, a Nature Conservancy project for salt marsh restoration, where they spoke to the US Army Corps of Engineers and said, you have this dredge spoil removal, this sand that you're just dredging, sand and mud, sorry, that you're just dredging, and usually what they do is they go far offshore and dump it. And the TNC is like, well, why not use that to reclaim a salt marsh that was lost? It's going to save you costs, and it's also going to restore this habitat that could provide risk reduction. And so things like projects like that are cases, sort of opportunistic cases where these two can come together. So I'm going to stop here. I've painted a very quick, very broad overview of the engineering. I'm going to next focus on a little bit on the communication. So essentially, from what I've said so far, engineers will have to work with other disciplines increasingly, especially if we're going to be, especially around the field of environmental science. For coastal engineers, this is engineering with nature, essentially combining your engineering goals with your conservation and restoration goals. And engineering with nature does work. It's just we need to be clever and think out of the box and also talk with other disciplines and work with other disciplines in order to figure out where and how and when this works. And this requires a fundamental shift in the way we think. And this shift is can be both challenging, but also exciting. So who cares? This is a very small subset of people within a subset of academia. Who cares about the work we do? How do we reach them? Well, the analysis that I did in India was this location here in Orissa. The site is it gets hit by cyclones every year, tropical cyclones. And the island that I was looking at, which is here, was right in front of a major port, a big port that was just being developed. And so I thought, hey, this is perfect. I mean, those guys are going to be very interested in what I do because it's their port. And they're sitting behind an island. And so I managed to wangle an invite to the port, went and made a presentation, and this is basically what happened. The civil engineer, I think, fell asleep 10 minutes into the presentation. I was like, oh, well, whatever. I mean, seriously, who cares? But since then, my view has changed. The project that I'm working on now, these are the people involved in it. So you have academia on the top row, you have research institutions and NGOs in the second row, you have foundations like the World Bank, the Rockefeller Foundation, you have the Army Corps of Engineers and the Department of the Interior working with us. And we also have private industry. So we have Risk Management Solutions, we have Lloyd's, we have CH2M Hill, which is a coastal engineering consultancy firm. And so there is a lot of interest around this, actually. And communicating what we do effectively is a big part of that. It's important to reach people in many different ways. So for instance, for the Hurricane Sandy wetlands work, we had a report, we had a press release, we had a video, we had a fact sheet, we had a blog post, and now we're trying to get a peer-reviewed paper in. And I think the key things here to remember are, the key things to ask ourselves in all of these are, who is your audience, what do they want to know, and what is your message to them? So for instance, peer-reviewed papers. The audience is usually going to be academics. The way you write it is going to be very different to sort of a report or a fact sheet because you're focusing on an academic audience who focus on the science and the process of what you do. Fact sheets, these are one-pagers. These are one-pagers that give you take-home messages, a map, and a very brief summary of what the work is that you're going to do. And these are targeted essentially at sort of at the client, so to speak, where you go, this is the work I want to do, you're a busy person, you have 5 minutes to read it and maybe be interested in it, and then maybe something will come out of that. We also have reports. So one really cool thing about the work that I've been doing is that it's taken me all over the world. This was a report that we did in Papua New Guinea, looking at the coastal hazards in 2 provinces in Papua New Guinea. We had workshops with the government officials, and we prepared a report. I want to, but at the same time, I don't want to know how many people read the report. But this is something that governments like. This is something that government officials like. We had press releases with the help of UC Santa Cruz, who drafted a press release for the report for Hurricane Sandy that we did, and then we did get a little bit of press coverage on that, which is always exciting. We have workshops as well, so it's not just writing, it's also going and having participative interactive workshops as well. And we also have an online tool. So I'm actually going to see if this works. Oh, okay. So this tool basically is, what we've done is we've taken this database of projects, nature-based projects that we collected, and we've put it online, and you can query it all across the globe by habitat, or by location, or by effectiveness. And we also had videos, and I am not sure how to get this video to work, so, oh, there you go. How would the sound for the video? Sorry. Yeah. Oh, there you go.
Let's put your mic.
Oh, fair enough. Yeah. So this is a video that we did in collaboration with a professional person in LA, just highlighting very briefly the work that we did for Hurricane Sandy.
Serious problem for communities around the world.
Can you hear?
In 2012, Hurricane Sandy struck the eastern United States and was the second costliest storm in U.S. history. Wetlands and marshes along our coastlines have been lost at high rates due to coastal development. In a new study, we worked with the insurance industry to put a dollar value on the flood protection benefits of coastal wetlands provided to communities during Hurricane Sandy. Using an engineering model, we calculated the storm surge and flooding impacts from Sandy. We compared the impacts of the storm to the coastline with wetlands and without wetlands. The results show us the protective value of the wetlands and their ability to reduce damages to property. In coastal areas across 12 states impacted by Sandy, wetlands reduced damages by more than $625 million. Because of the wetlands, the damage to Maryland's coastal communities was 30% less. And in New Jersey, wetlands saved more than $400 million in assets from damage. This study and partnership between conservation, academia, and the risk industry showcases the value of our wetlands as natural defenses, suggests potential financial incentives for government, business, and individual property owners, and supports new approaches for restoring our protective coastal ecosystems. When the next hurricane strikes, healthy coastal wetlands can play a key role in better protecting our coastal communities and economies.
Yep, so thank you. Happy to take questions.
Thank you. What a great talk. So questions? Luke?
You've talked today about the economic benefits or the reduction in property damage to human structures by putting in potentially these biological buffer zones. I wonder if you could also speak a bit about the ancillary benefits, particularly economic benefits that you get from having not a concrete seawall, but something, a mangrove, salt marsh, et cetera.
Yeah, absolutely. That's a very good question. So the way we've approached this is that we're saying these marshes, these ecosystems, these wetlands have this risk reduction benefit, and this is only going to be one of several benefits. So if we're going to say from a coastal engineering point of view, if we can say that this is effective from a risk reduction perspective alone, the benefits are huge beyond that if you start including every other ecosystem service. Like for instance, there were studies in Vietnam, there's this giant mangrove restoration project in Vietnam where the risk reduction benefit was actually a very small part of it, and they didn't get much from that. But then when they included, say, tourism and fishery enhancement and water quality enhancement, the benefit cost ratio went up to like 16 or something from almost close to 1. So yeah, it is absolutely essential to remember that this is just one, and in many cases, not even the main. But in some cases, it is probably the most, sort of the biggest chunk. Yeah.
You were mentioning how expensive it can be to build these different coastal projects. How much money could be saved by, say, implanting like mangrove in front of those structures, and just the cost-benefit analysis of that?
So yeah, so that points to the hybrid structures that we were talking about, and that's like becoming. I mean, there's increasingly a lot of focus on that, and a realization that we're not going to be able to protect ourselves just with nature. We're going to have structures. For the storm surge barriers that I showed, you won't even have ecosystems in those areas. So I mean, the storm surge barriers are massive. They're meant for things that the ecosystems are like massive storms that the ecosystems probably won't even help with. But for instance, with waves and with flooding where you have space, there are a few studies that have showed that having, say, 300 or 800 meters of mangrove or salt marsh before a seawall can reduce the height of your seawall by 1 meter. And if you're going to extend that along the coastline, that can translate to huge benefits, because the height of your seawall is the primary cost component. Like, that's what determines the cost. So yeah, definitely.
I was interested in your coastal resilience website, and we'll certainly make the link available for all the students. That website, how's it developed? Does it have connection with a lot of other web-based projects? Does it have real-time data feeding into it? How did that get developed?
So that website has really grown into something huge. Yes, it does pull information from a lot of other websites. So for instance, there are layers that you can view on global or US specific hazards and risk indices that it pulls from I think UNISDR, but also, I'm blanking on the name right now, but this institution in Zurich that have global information on hazards and risk indices, but also pulls layers from, say, the World Bank Poverty Index or the GDP Index, things like that. Yeah, and you can, like, pretty nifty exploration tools.
And I think we have a final question.
So you have on the screen there quite a few organizations, and you mentioned before you do a lot of collaboration with government, with industry, and I'm wondering how those partnerships have developed. Did it start with a small group and then expand, or do these people come and approach you?
So initially, for me, I'm going to answer this from my perspective initially. So I came here to the US, to Santa Barbara actually first, for a SNAP, Science for Nature and People postdoc. And SNAP is this consortium organized by UC Santa Barbara, so NC's National Center for Ecological Analysis and Synthesis at UC Santa Barbara, along with TNC and the Wildlife Conservation Society, they've come together to create these 2-year-long working groups. And so I was here for a 2-year-long working group on coastal defenses, which was one of the first SNAP working groups. And within that working group, we had invited people from RMS to be on our advisory board. And we were having a conversation with them where we said, you guys are doing insurance risk modeling. Do you account for coastal ecosystems? Do you account for, say, the effect of mangroves? And the RMS guys were like, I actually don't know the answer to that. So they didn't know if their models were accounting for ecosystems. So we're like, let's look into it. And so it turned out that their models, actually the way the model is built, it did account for these ecosystems in terms of a friction coefficient parameter. It just did not parse them out, and it did not they were lumped in with several other factors. And so from that, the idea was born to do the Sandy project, which we then went to Lloyd's with and said, we're going to investigate how insurance models include coastal ecosystems. And we're going to do that looking at the US Northeast. So there was already a group, but I feel like that sort of builds on itself in some ways. So that's essentially how it's been for me. Yeah.
Thank you very much, Dr. Sid Narayan.
Thank you.
I think Sid will probably stick around for at least 10 minutes if you'd like to come up and chat with him.